Okay, now we want to grade this one. This one is going to be a little bit weird. I apologize in advance for that. It's going to be kind of. I'm just going to say it. It's going to be unsatisfying. Yeah, it's just going to be an unsatisfying answer. Sorry, I have not found a very good way to write this solution. So if you guys have something else, I would love to see it. But this is just one of the. This is just a PDE where there's not a great like closed form solution for it, and even including the fact that in the other ones, our answers involved an integral. We get something even worse than that in this case, because we're going to have a double integral, as we will see. Okay, so take Fourier transforms. Okay, so on the left-hand side, we'll get the t derivative. And on the right-hand side, it's going to be I omega cubed. Well, that's I omega squared times I omega. I omega squared is minus omega squared. Multiply that by I omega, it's minus I omega cubed times the Fourier transform, whence. Okay. Okay, so then we've got this is equal to the initial, the Fourier transform of the initial data times e to the minus I omega cubed t. Well, what can we do at this point? There's not. So the inverse Fourier transform is going to be the convolution of the inverse Fourier transform of both of those, or something. We could just do the integral with the inverse Fourier transform. So there's a number of ways we can do this. I want our answer to have f there instead of f hat. So there's two ways to do this. We could either say that the solution is just going to be, we plug this into the formula for the inverse Fourier transform. That would be completely correct. But I would rather have our solution be explicitly in terms of f rather than the Fourier transform of f. So it's going to be the convolution of f, which is the inverse Fourier transform of that, and then the inverse Fourier transform of that, which I'm just going to use the formula for. So we're going to have u of xt is equal to the convolution of these two. It's equal to 1 over the it's equal to 1 over the square root of 2 pi of the convolution. So now we're going to have the integral y equals minus infinity to positive infinity f of y, and then on the inside I'm going to put the integral for the inverse Fourier transform of this. So I'm going to come down a line here. So now this is going to be the integral from omega equals minus infinity to omega equals positive infinity. It's going to be this function here, and then e, we need to be careful here, it's going to be I omega, but the variable, since I'm doing the convolution, is not going to be x, it's going to be x minus y here, because that's what the convolution is. Okay. Okay, so we have this. Now there is a problem because I didn't do this. Okay, now there's a problem here because this is a modulus 1 thing for all values of omega. This is a modulus 1 thing for all values of omega. So this does not seem to completely make sense. So to be a little more precise, to at least give something that maybe has a chance of being well defined in terms of Fourier transforms, we're going to have something like this. Okay, so really what I'm saying is this e to the minus I omega cubed t, like this is a distribution that we need to figure out, what it means to take the Fourier transform of. We don't exactly know that right now, so just in terms of Riemann integrals, improper Riemann integrals, we have something like this. Okay, and now if we want, and I don't see any reason not to, I'm just going to write this as, so this is just, not only is there, so this is not great because not only is there two integrals, there's this limit that's going on as well that I somehow just messed up. I just want to copy and paste this whole thing. Okay. We're going to have this. Okay, so let's get rid of this. Let's get rid of this. And then I want to go ahead and put the f on the other side of the integral. So I'm going to have it like this. And again, at any point, I mean, since this is, there's sort of some not well-definedness to how I want you to answer this. Basically, anything that is getting anywhere in the ballpark is going to be correct. But definitely, you don't need to kind of modify it as much as I'm doing it here. I'm just kind of modifying it to get to a point that looks the least bad. And I don't really have a good definition even for what that is. Okay, I think we're going to have something like this. Now notice what you can do here. You can kind of split this up, and the inside integral here really ends up computing the Fourier transform of f. So I had a problem with just applying the inverse Fourier transform to that because it was only in terms of the Fourier transform of f rather than the inverse. Sorry, it was only if we had just taken this. So let me just actually write that. Another way to do this is to take the inverse Fourier transform of this directly we get u of xt equals and then it's going to be this times e to the I omega x d omega. Okay, now this might look a little bit better in terms of integrability. See up here, the issue is that this omega integral going from minus infinity to positive infinity, this does not look like an integral that is going to make sense. For example, when y is equal to x, this is 1, and we're just integrating this, and that definitely does not converge in any meaningful sense. So we can only view this as a distribution. Now down here it might look a little bit better because we also have this f hat of omega. But remember, just because f is integrable doesn't necessarily mean that its Fourier transform is going to be integrable. Because remember, we have this principle that if we have a small Fourier transform, we have a big, sorry, if f is small, its Fourier transform is big, where big and small mean different things. But what we do know, well, sorry, I don't know what I was about to say. So for example, the Fourier transform of the rectangle function is integrable. It's just equal to 1 from minus 8a and 0 everywhere else. So that's integrable, but its Fourier transform is this sine omega over omega function, which is not integrable. Okay, in the sense that its absolute value is not integrable. At any rate, we can keep it like this, or to keep it consistent with what we have up there, I'm going to write this, the limit as n to infinity. Yeah, so this is one, like I said, the answer, unfortunately, just is not very satisfying. And the other thing that I was going to say is if you take the e to the I omega x and e to the I minus omega cubed, if you take that out because it doesn't depend on y, what you end up doing here is this: you're computing the Fourier transform of f. Or even if you keep the x there, you're computing the Fourier transform of x minus y, and now you have the same exact formula. Okay, sorry, that part was a little bit rambly. I guess a lot of it is rambly because I'm just talking to my computer, and it's my thoughts, which gets kind of stream of consciousness. All right, that is the solution, as unsatisfying as it is. Like I said, if you have a better way or something clever, a clever trick here that I just haven't thought of, I'd be interested in seeing it. So talk about it in the discussions.